So we are back to the slides from the Excel calculator, and we have learned some lessons. One is that the material characteristics remain the same for both the P side and the N side because it's the same semiconductor. The built-in voltage, which is the delta E sub F, the difference between the Fermi levels on the P side and the N side, is given by kT divided by Q, natural log of N sub A, N sub D, divided by the square of the intrinsic carrier concentration. And the width of the depletion region at equilibrium because of the built-in potential V naught is given by the expression of W naught. And this is doping dependent. So you see within the expression N sub A and N sub D. And obviously you see V naught. But it's also material dependent because you see the permittivity of the semiconductor within that expression. And finally, the Excel sheet does not take into consideration any bias voltage, forward bias or reverse bias being applied to the PN junction. So the Excel graphical calculator considers simply the equilibrium conditions. Now we move to heterojunctions, and we know that from the Excel calculator that at the junction we would have fixed ions that form charges and a charge density. There is an electric field, there's a potential that's caused because of the electric field, and so the energy band diagram of the PN junction forms. But in case of a heterojunction, we can quickly see from the figure on this slide that there could be three scenarios. The first type is the straddled or nested heterojunction, in which the energy bands of the narrow band gap material lies within the energy bands of the wider band gap material. The second type is called the staggered heterojunction, in which the conduction and valence bands of one material is either above or below the corresponding conduction and valence bands of the second material. And the third type is the broken heterojunction, in which the conduction bands and the valence bands, or the entire band structure of one material is either above or below the entire band structure of the second material. So looking at this figure, we can quickly conclude that while V naught continues to remain delta E sub F, which is the difference in the Fermi levels of one material and the second material, but it is not equal to kT over Q natural log of N sub A, N sub D divided by the square of the intrinsic carrier concentration, because the intrinsic carrier concentration would be different on each side. We can also quickly conclude that the W naught expression of the PN junction is no longer valid because the materials are different. We also can conclude that the electron affinities on either side are different. Also, the band gap of one material is not equal to the band gap of the second material. So the band gap on the left side is not equal to the band gap on the right side. And therefore, there is a delta E sub G. Same with the conduction bands and the valence bands. The conduction band and the valence bands on the left side are not at the same levels as that of the right-hand side, causing delta E sub C and delta E sub V. So what would be the expression for the built-in potential and the width of the junction for a heterojunction? Well, we can start off at the basics where V naught is equal to the change in the Fermi level energies of each of the materials, and therefore is equal to the work function of the P side minus the work function of the N side. And this is valid for all the three types of the heterojunctions shown in the figure on this slide. We plug in the values for the work function of the P side and the work function of the N side and get the second expression on this slide. And finally, we get the third expression on this slide. The green colored part of this expression is very similar to the PN junction. The blue part comes from the differences in the electron affinities of the two materials and hence the difference in their respective conduction band energies. The orange term takes care of the difference in the band gaps of the two materials, and the gold term takes care of the differences in the density of states in the conduction and the valence bands of the two different materials. Now, note that one could argue that V naught is the work function on the N side minus the work function on the P side. And that's a valid argument. Now, once if you try to do that, then the signs of delta E is going to change. And so based on the reference given on this slide, we have concluded that the signs of delta E should be taken with a grain of salt. So cum grano salis. The expression for the width of the junction W naught is also given on the slide, and the expressions for the widths of the junction on the P side and the widths of the junction on the N side is also given on the slide. What is important to note here is that the permittivity of the two different materials have been taken into consideration in the formula. The formula also includes doping concentrations of the two different materials alongside their respective permittivities. In addition to the difference in the formula for V naught and W naught for heterojunctions, we have to consider further complexities when dealing with heterojunctions. The first such complexity is doping. So we could have a PN heterojunction, we could have an NP heterojunction, but you could also have an NN heterojunction or a PP heterojunction. And it is quite possible that the doping on one side of the material or one of the materials is much higher than the doping in the other material. Further, what about intrinsic materials? And if intrinsic materials are combined to form a junction, we would have to take into consideration the band gap. So the flow of the carriers between the wide and the narrow band gaps need to be taken into consideration. And all this that we have talked about so far with regard to doping is to try to figure out where the Fermi level is going to pin itself in case of the heterojunction. The second consideration is material. So usually when we talk about junctions, we might assume that we are talking about an inorganic material forming a junction with another inorganic material. Uh, but it could be an inorganic material forming a junction with an organic material. And what are the complexities that we need to take into consideration when that happens? We are going to see that in the coming slides. And the materials could be both two different organic materials. The third consideration is alloying. And we do know that alloying could change the band gap of the material that is being alloyed. In case of heterojunctions, this could possibly change even the type of the heterojunction. So we are trying to analyze the figure given on the slide that's taken from the reference given below on the slide as well. And you can see that when magnesium is added to zinc oxide, the band gap increases by 1 electron volt, and it is entirely the conduction band that moves up. Now, if the conduction band moves up by 1 electron volt, it means that the zinc oxide heterojunction with 6p has moved from type 2 to a zinc magnesium oxide heterojunction with 6p, which is a type 1 heterojunction. And this means that a type 2 material that enables the dissociation of excitons into electrons and holes for solar cell applications could be changed by simply alloying the material and forming a type 1 heterojunction. The same materials could now be used in a LED or light emitting diode application. So the electrons and holes could flow into the narrow band gap material and recombine radiatively. The fourth consideration is the crystal orientation during growth. As you could see in the figure taken from the paper in the reference, the delta EC in figure A is different from the delta EC in figure B. The delta EVs are different, and even the work function from the vacuum levels are different. And all this is simply because the zinc oxide was grown in a different crystal orientation, which in turn affected the orientation in which the 6p was deposited on the zinc oxide. So the crystal orientation during growth plays a crucial role in the heterojunction characteristics. Another consideration would be the interactive nature of interfaces seen in a case of inorganic and organic heterojunctions. The figures on this slide are taken from the paper in the reference. And on the left side, you see the individual band diagrams for indium phosphide, alpha NPD, and copper phthalocyanine. Analyzing this, we could conclude that both the organic materials would form a type 2 heterojunction with indium phosphide. In case of indium phosphide and copper phthalocyanine heterojunction, we do get a type 2 heterojunction, but it is not as what we would have expected because the delta EV is much smaller. And in case of indium phosphide and alpha NPD heterojunction, we get a completely unexpected type 1 heterojunction where the valence band or HOMO of alpha NDP has fallen below the valence band of indium phosphide. And so the reason why this happens is because there has been an interaction between the inorganic and the organic compound at the interface. So the reaction that happens between the inorganic and the organic compound just at the interface needs to be taken into consideration when we are dealing with the kind of heterojunction that may be formed between inorganic and organic materials. In practice, the band diagram, the band energy diagram for the heterojunction is measured via experiments. The most common experiments are photoemission spectroscopy and optical absorption spectra to figure out the values and parameters that would show how the bands line up at the junction. And obviously these values help in forming a more accurate shape of the heterojunction. In fact, the experimental methods of figuring out the band diagram for heterojunctions are by far considered the most accurate method for measuring the band diagrams for a heterojunction. In addition to the experiment methods, there are several numerical calculation methods of figuring out the band diagram for a heterojunction. The accuracy of all these calculation methods, numerical methods, are debatable, but people are fairly content with the shape that comes out through these methods. One of these methods is the electron affinity rule introduced by Anderson in 1962, which essentially states that the difference in the conduction bands of the two materials is conserved in the heterojunction. And the same is true for the difference in the valence bands. Another method is based on the bulk band structure introduced by Frensley and Kromer in 1976, which makes use of three different pseudopotentials found in the bulk of a semiconductor to predict the discontinuities at the heterojunction. Another method introduced by Kromer et al. In 1980 was to make use of a numeric capacitance voltage profiling for the heterojunction to measure the band structure. And additionally, we have the density functional theory DFT calculations that could help form the structure of the heterojunction. Once again, it is important to note that in the science community, the accuracy of these numerical calculations is debatable. But people and the science community is fairly content with the shape of the band diagram that comes out as a result of these numeric calculations. So if we want to proceed to make a simple Excel model of the band diagram for a heterojunction, we would have to consider certain inputs to empower the user. These include the ones that we saw for the simple PN junction. To choose the left side and the right side as either N-type or P-type, the doping concentrations, N sub A and N sub D, and the specific material characteristics. In addition, we would have to consider doping. So the left side and the right side could be the same type, such as both of them could be N-type or P-type, just varying doping concentrations, or even intrinsic. Material characteristics such as the intrinsic concentration, um, the density of states, electron affinities, band gaps, and relative permittivities are going to be different for the two different materials. And the materials could be both inorganic or both organic, and could be a combination of inorganic and organic. We would have to consider the effects of alloying, crystal orientation during growth, and the interactive nature of interfaces, particularly in inorganic and organic heterojunctions that we discussed in this presentation. Okay, so we have seen the importance of the junction, its formation, its content, which is the charge, electric field, potential, and this leads to the energy band diagrams. We saw the p-n junction, which is fairly straightforward, but when we want to build a simple Excel model, we have to make some careful considerations. The heterojunction is complex, and it requires further considerations in building a model. There are several calculating and prediction models, but their accuracy is debatable. And the models help in forecasting the shape, but it is the experiments that help in attaching accuracy to that shape. There are several models that require downloads and installs or use of specific software techniques such as DFT. However, the simple Excel model is easy to use, but it allows for a basic shape of the band diagram only. So the next steps would include characterizing the simple heterojunction model using Excel, simply because of its simplicity and accessibility, and to make the required considerations as was discussed in this presentation. Then the idea is to compare the Excel model with other complex models to check for conformity with the shape of the heterojunction band diagram that we get. And further, to perform experiments on the materials that we use to build the heterojunction in practice, and measure such characteristics once again to confirm or to check the conformity with the shape of the heterojunction band diagram that we would get from Excel. Thank you to Dr. Adrian Kitai, my professor and supervisor, for his continuous feedback, encouragement, guidance, and mentorship towards heterojunctions. And thank you to Sam Peter for his continuous constructive feedback that helps me continue and progress with the Excel model. And thank you for listening to my presentation. There are a number of backup slides that are going to follow this video. These backup slides include the formula that has been used in the simple Excel graphical calculator, along with the meaning of those formula. Thank you very much. Stay safe, stay healthy. Thank you.